In 2.12, we're asked to find the expectation values of xp, x squared, and p squared, and t for the nth stationary state of the harmonic oscillator, and we're specifically asked to use the example 2.5 method. And then we're asked to check that the uncertainty principle is satisfied. So example 2.5 had us solve for the expectation value of the potential energy for the nth excited state. And the method that we used in 2.5 was that we decomposed x and p hat into sort of these equations that used the ladder operators. So x could be described in this case in terms of ladder operators as the square root of h bar over 2m omega multiplied by a hat plus a hat minus, and then p hat was respectively a hat plus minus a hat minus with an extra I term and this reciprocal of square root of h bar m omega over 2. And then we took advantage of the fact that a hat plus a hat minus acting on psi and a hat minus a hat plus acting on psi behaved in ways that we could predict using these formulas. So let's do this, but this time instead of doing it for v, we do it for all of these terms. So first off, let's start just by expressing x squared and p squared in terms of these ladder operators. So if x is this, then x squared has to be just this applied twice, so the constants at the front just get squared, so this becomes h bar over 2 omega. And then we have a hat plus a hat minus squared, which becomes a hat plus squared plus a hat plus a hat minus plus a hat minus a hat plus a hat minus squared. And the reason why we're not combining these is once again because ladder operators, or just in generally operators, are not necessarily commutable, so these two don't necessarily equal the same thing. And then let's do the same thing for p. So p hat squared is going to be equal to this term right here squared. The two i's make a negative, so we have negative h bar m omega over 2. And then we have the same thing, so a hat plus and all this stuff, with the difference being that the two terms in the middle here become minuses. Okay, now let's actually find these expectation values that we're asked to find. So the expectation value of x is going to be equal to the integral from negative infinity to infinity of psi n star times x times psi n dx. If we want to express s or x in terms of this operator, then we write it as the square root of, let's see, h bar over 2m omega multiplied by the integral from negative infinity to infinity, and then the sort of x position states, the stationary position-based states for the harmonic oscillator are all real, so the complex conjugate is just exactly equal to the real component. We can just rewrite this as psi n multiplied by, let's see, a hat plus a hat minus. And then this is acting on psi n again, and we close this integral with a dx. So hopefully immediately you see that this is just going to equal 0, because if we split this into two component integrals, we have an integral of psi n times a hat plus psi n, and then another integral of psi n, and then a hat minus psi n. So the a hat plus and a hat minus respectively will change the psi n to the right to psi n plus 1 and psi n minus 1 with like whatever constant is at the front determined by these formulas. But the problem is that we already know that the stationary states are sort of orthogonal to each other, so any integral from negative infinity to infinity of psi m star times psi n dx is going to be equal to a Dirac delta function in terms of m and n. So m and n have to equal each other, in which case this integral becomes 1, and if they don't equal each other, then this has to equal 0. So therefore, we have two sort of integrals where m is equal to n, and n is equal to either n plus 1 or n minus 1. So because of that, m and n are not equal for both of the integrals in this case, and this is just going to equal 0. The exact same thing is true if we try to find the expectation value of p, because p is the exact same thing, just with a different series of constants at the front, and then a hat plus minus a hat minus, instead of a hat plus plus a hat minus. Ultimately, that's the same thing. It's the same exact scenario. It's just our two integrals are getting subtracted from one another instead of adding onto one another. Regardless, the central idea is that we're having psi n acting on either psi n plus 1 or psi n minus 1. And in both cases, this integral resolves to 0 because of this whole orthogonality rule with Dirac deltas. Okay, now that we know that the expectation values of x and p are both equal to 0 respectively, we can do the same thing with x squared and p squared. And hopefully you immediately see a pattern here, because we have a hat plus squared and a hat minus squared in both x squared and p squared, and these components of the integrals will also go to 0 respectively, because we're going to be dealing with an integral from negative infinity to infinity of sort of psi n multiplied by either psi n plus 2 or psi n minus 2 for the a hat plus and a hat minus case respectively. So we can automatically sort of expunge these from our integrals, and what we're left with is that the expectation value of x squared is going to be equal to this constant at the front of h bar over 2m omega times the integral from negative infinity to positive infinity of psi n multiplied by this a hat plus, a hat minus, and a hat minus, a hat plus term. So these are the only ones we don't actually discard. And the reason why we don't discard them is because a hat plus a hat minus acting on psi n returns it to just psi n again, but just with some new constant at the front. So because of that, we actually do keep these, because these integrals don't go to 0. We close this off with a dx, and then we use this formula. So we know that a hat plus a hat minus goes to n, and a hat minus a hat plus goes to n plus 1. So this is actually effectively the same thing as h bar over 2m omega times the integral from negative infinity to infinity. And then let's split this into two terms. So let's start with this first one, which is a hat plus a hat minus acting on psi n. So this is psi n times a hat plus a hat minus acting on psi n. We know that a hat plus a hat minus acting on psi n gives us n psi n. So psi n times psi n. And then we add, and then here we have psi n, and then a hat minus a hat plus acting on psi n, and we know that that gives us n plus 1 times psi n. So psi n plus 1 psi n. And now we just use distributive property. This is going to be equal to h bar over 2m omega. And then we bring out the constants, which is the n and n plus 1, so this becomes 2n plus 1. And then we have our integral from negative infinity to positive infinity of the magnitude of psi n squared dx. And this, by definition, since it's already normalized, is just equal to 1, so therefore this is our sort of expectation value for x squared. We do the exact same thing for p squared, so we get the expectation value of p squared to be equal to, and once again, we can sort of just ignore the plus squared, a hat plus squared and a hat minus squared terms, because their integrals will go to 0 due to orthogonality. And what we'll see here is that this gives us the exact same result, because we can factor this minus back into sort of our parentheses, and we'll get minus plus plus minus. And if we're ignoring the a hat plus and a hat minus terms, then this is exactly identical to the x squared. So in reality, this is just equal to the same constant at the front, so h bar m omega over 2. And then sort of this a hat plus a hat minus a hat minus a hat plus thing gets evaluated in the exact same way as we did in x. So this is just going to give us the same term of 2n plus 1. And then the same integral as above here, which evaluates to 1 again. And thus, we have the expectation values of x squared and p squared, respectively. Now that we have xp, x squared, and p squared, the only thing we still need is t. And we already know from sort of the previous problem that we can express t in terms of the p operator and get that t is actually, or the expectation value of t is actually just equal to 1 over 2m times the expectation value of p. Because p is equal to mass times velocity, so, or mass times velocity squared, apologies. So we sort of t can be expressed in terms of p instead of v. So instead of 1/2 mv squared, we can just do p over 2m. So, or sorry, p squared, not p. And then we already have p squared, so this is just equal to 1 over 2m multiplied by this. So this becomes h bar omega over 4 times 2n plus 1. And that is the expectation value of our kinetic energy. Finally, we're asked to check that the uncertainty principle is satisfied. We already know how to do this from the previous problem. Hopefully at this point this is just a trivial exercise. The uncertainty in x is going to be equal to the square root of the expectation value of x squared. Since the expectation value of x itself is just 0, so that term doesn't come into play. This is going to give us the square root of h bar over 2m omega times 2n plus 1. Similarly, the error in p is going to be the exact same thing. It's going to be the square root of the expectation value of p squared. So this is going to be equal to the square root of h bar m omega over 2 times 2n plus 1. And then verify the uncertainty principle, which is to show that the standard deviation in x, or the error in x, times the error in p has to be greater than or equal to h bar over 2. So if we multiply these two together, whoops, I forgot to erase this. Yeah, so if we multiply these two together, what we're going to get is the h bar comes outside, and then also the 2n plus 1 comes outside, because these are sort of common terms for both standard deviation in x and standard deviation in p. What we're left with is m omega at the top and n omega at the bottom, which both cancel, and then 2 at the bottom for both, so that comes out as well. So h bar over 2 times 2n plus 1. And this does indeed sort of satisfy the uncertainty principle, and it also agrees with sort of the problem, the previous problem, which was problem 2.11. Because in the previous problem, we found that the product of the error in x and the error in p for the n equals 1, or for the n equals 0 case, was equal to h bar over 2. And if we plug in n equals 0, we see that that's true. And then we also found that the energy for the excited state for psi 1 was equal to 3/2 h bar, which we also find is true, because if n equals 1, then this is 2 plus 1, which becomes 3, so we have 3/2 h bar. And overall, the uncertainty principle is always satisfied, because the smallest possible value for the uncertainty principle is going to be when n equals 0, which gives us the h bar over 2 value, which is the minimum value of the uncertainty of these combined uncertainties. And as we sort of go up to higher states, the product of the error in x and the error in p just gets larger.